it's a pleasure to introduce Anurag Rao, and he'll be telling us about a theorem of Davenport and Schmidt and its improvement and on Dirichlet-improvable pairs. Okay, I was going to say something nonsensical. Go ahead.
Okay, yeah, so thank you. And let me apologize in advance if my internet drops off at any point. Please stop me if you see that I'm talking and my slides stop moving or something like that. But yeah, I'm here to discuss some work in metric Diophantine approximation, and it's based on joint work with Dimitri Kleinberg. Okay, so what is metric Diophantine approximation? So it deals, this is an area of math which deals with some asymptotic properties of real numbers with respect to the rational numbers. So for example, you can take a real number x and consider this quantity. You're looking at the limits as q goes to infinity over the natural numbers of q times the distance of qx from z. So you've got x, some real number here. You're looking at its integer multiples, and then you're seeing how close 3x or 2x is to the integers. And then you're seeing what this quantity becomes, in limits. So what's the smallest subsequence of natural numbers that you can have, such that the limit is smallest. Now you can see that this is related to how x is approximated by rational numbers by rewriting this thing in here as q times qx minus p. So this distance is attained by some integer p, and then maybe you can even pull out the q and get x minus p over q. Oops. So we're considering some kind of approximation of x by rationals, and we're comparing the error of x minus this rational with the denominator of the rational. So roughly that's what that's something that you can do in Diophantine approximation. Okay, so for rational x, this limit is always going to be 0. On the other hand, for irrational numbers, since most irrational numbers have tenuous definitions themselves, it's actually hard to compute what this quantity is going to be. So instead, the business here, so metric Diophantine approximators, prove proto-theorems that look like this. So for every real number x,
can I ask you a question, Anurag?
Lx, yeah.
Is it obvious that this Lx is finite for irrationals? So
no. It's obvious. Maybe 2 slides later it'll become obvious.
All right. Okay, we can wait till then.
Yeah. So yeah. Okay. So yeah. Let me state the theorem, and then I'll maybe give another hint of like how to see that this is even finite. Okay. So we can do more than finite. In fact, for every real number, Lx is less than 1 over square root 5. The upper bound is sharp. There are real numbers for which this is exactly 1 over square root 5. The typical behavior in terms of probability is that Lx is going to be 0. On the other hand, the set of numbers for which Lx is greater than 0 is very large. Of course, Lebesgue measures 0, but Hausdorff did mention 1. So you'll see all of this in maybe a first course on continued fractions. So maybe that's one way to see that this is finite, and then maybe this as well. But we'll see another way. Okay, I guess right here. So the theme of this talk is Dirichlet's theorem. So what it says is, if you take any real number and any time greater than 1, then this system, where you take x and you take some q multiple of x, compare it with the distance with the integers. Well, okay, maybe I should rephrase that. So what this means is, for any t, I can find an integer q, absolute value less than t, such that if you go you know, qth iterates of x, and you compare with the integers, the distance or the error is going to be 1 over t. So this is again some kind of Diophantine property of x, and multiplying these together, you get something related to the quantity we saw on the previous page. So it's very easy to see that q times this is less than 1. That has infinitely many solutions in q and p. Another formulation or another version or a generalization of Dirichlet's theorem is where you can consider, rather than real numbers, vectors, two-dimensional vectors in R2. And you can again look at the solubility of this system. And Dirichlet's theorem says that you can always find P in Z2 and Q in Z minus 0 such that you can solve this. So maybe the picture to keep in mind over here is that you have some X and you're taking qth multiples of X, and then you're comparing with the standard lattice. So the standard lattice looks like this. Okay. And if you're wondering how to prove these things, well, maybe one hint is Minkowski's convex body theorem. Okay. So this is the theme of our talk. And now we can finally get to—
Sorry, can you go back to your previous slide? So,
yeah.
So I'm just trying to make sure I understand this. So just Dirichlet's theorem. So let's look at that.
Sorry, yeah.
Yeah. So Dirichlet's theorem is telling me that I have a bound on the denominator, and now you're saying that I'm going to try to approximate my real number x by a rational with this bound on the denominator, and I can actually you can give me a good approximation in the sense you will get something like 1 over q squared is the bound you're getting. So this will show me that L of x in your previous slide is actually bounded by 1.
Mm-hmm.
Right? Okay. Okay.
Yeah.
That's what I wanted to clarify. So 1 over square root 5 probably requires much more more arguments, I guess.
Yeah, maybe it's very classical, but yeah, it is involved. It's well known, but slightly involved. So you can see it by continued fractions or by geometry of numbers. So it's like well known, yeah.
Right, and the second theorem is sort of a higher dimensional generalization of the same thing. So can I think of it as you are trying to approximate two irrationals simultaneously? Is that how I should think of it, or should I think about it as the way you were describing it, approximation of lattice points in approximation by lattice points? How should I?
So right now, just think of it as simultaneous approximation.
All right.
Yeah. Okay. So essentially, this is what we're going to focus on in the talk. This theorem D2. Okay, and I just realized there might be some lag with my scrolling and my highlighting, so I apologize for that. Okay, but Davenport and Schmidt were looking at this system, and they, asked the naive question: what happens if you try to reduce this 1 over square root t by some constant times itself for some c less than 1? And they gave this definition that x is said to be directly improvable. X belongs to di infinity. If there exists c less than 1 such that this system can be solved. So I'm writing max here, but it's essentially the same as combining these two conditions. It's exactly the same thing. Okay, so x is directly improvable if we can solve this system for all sufficiently large d. So there's some trade-off about using strict inequalities and then adding one more quantifier, but essentially it's kind of the same thing. We want this system to be solved eventually. It's some kind of uniform condition that we want to hold for all sufficiently large D. So maybe in other words, you can rephrase this condition by maybe multiplying them together, and then you see that X is Dirichlet-improvable if and only if this quantity C infinity X defined as the lim sup of this thing is less than 1. So again, this is some kind of Diophantine invariant of X, and this being less than 1 is equivalent to X being Dirichlet-improvable. This is the set of numbers that Davenport and Schmidt were studying. Okay. So the infinity here just denotes that we're using the sup norm distance. So when we look at Qx, it's a vector in the plane. So Qx is going to be somewhere here, and then the neighborhoods are just going to be sup norm balls, which are squares. Forgive the drawing. And here's the metrical or probabilistic theorem that they proved. This set, di infinity, subset of R2, it has Lebesgue measure 0, but it's definitely non-empty, it's definitely uncountable, and in fact, it has Hausdorff dimension 2. So if you're wondering what Hausdorff dimension is, it's basically a dimension function whose domain is not just submanifolds of R2, but it's any Borel set in R2. So of course, it agrees with our intuition of dimension. So this is going to be dimension 1. This is going to be dimension. This is dimension 0. This is dimension 1. The plane is going to be dimension 2. But there are Borel sets which have even fractional Hausdorff dimension. So if you have some kind of Brownian motion, this might have dimension 1.5 or something like that. So it's a very robust dimension function. Now, I don't even know how to draw this di infinity because apparently it has Lebesgue measure 0 and it has Hausdorff dimension 2 everywhere. So it's in fact dense, and at every point locally it has full Hausdorff dimension. So more than dimension 1.5. So a very strange set, and this is what they proved.
So is it connected by any chance, or do you have any idea about the topological properties of this set?
No, I mean, no.
Like it should not be connected. I am sort of imagining that it should be some sort of a Cantor set, but then at the same time, I can imagine that if I take a point which is badly approximable, and if I nudge it a little bit, okay, something to think about later.
Yeah, that hasn't crossed my mind. I mean, when you say it looks like a Cantor set, people definitely have constructed Cantor sets inside this bad too. I mean, that's how they that's one way of maybe showing they have
the Hausdorff dimension is 2. Yeah.
Yeah, but exactly what it is, I have not much clue, yeah, about this other topological properties. Okay. So let me say that this Hausdorff dimension result was kind of proved indirectly. What they showed was that this classical, slightly more classical object called the set of badly approximable vectors X in R2 is a subset of di infinity. And Schmidt had earlier studied this set and shown that this set has dimension 2. So automatically di infinity also has dimension 2. So badly approximable vectors go back to maybe even the 20s and 30s where they were studied. And one definition of badly approximable vectors is this. It's the same kind of definition as similar kind of definition to di infinity, except you're taking a lim-inf over here, and stipulation is that the lim-inf is greater than 0. So this is some kind of, asymptotic. You want something to hold for infinitely many q, whereas on the other hand, we wanted something to hold uniformly after a certain point. So yes, Schmidt had written this very foundational paper on Schmidt games, where he proved that, or a second foundational paper on Schmidt games, where he had already proved that dA has dimension 2. And then there was some argument that they wrote down, and they showed that dA is actually contained in Di infinity. And the Lebesgue measure 0 was again slightly. So it was in a different paper, and it was some work. Okay.
So just to go back to continued fractions.
Yeah.
So just to go back to continued fractions, if you were looking at R, then we would be looking at things which have arbitrary large coefficients in my continued fraction expansion. That would be the badly approximable number. No, the ones which have bounded. Yeah. The ones which have bounded would be badly approximable. And okay, and that you're saying implies the fact that
I didn't say anything. I didn't say anything about continued fractions in R2. I don't even know what. I don't.
Right. I'm just trying to see if this is obvious in in dimension 1. So that if I'm badly approximable in 1, then I have that the bound is less, that the lim sup is less than 1.
It's in the same paper where they did this one-dimensional problem as well, and it's not completely trivial. I mean, you have to do something with the remainder of this remainder term of this continued fraction approximation and do something.
I see.
But it's all written well in the 69 paper.
Okay.
Yeah. And if you want an updated version, there's a work by Kleinbach and Wadley which does the one-dimensional thing as well. Okay, so this set of Dirichlet-improvable pairs introduced long ago, but they fall under the category of uniform Diophantine approximation, and they've received not as much attention as asymptotic Diophantine approximation or asymptotic Diophantine invariance. So it's well known that Di infinity contains badly approximable vectors and singular vectors. I won't define what these are, but it's not clear what else. The exact structure of Di infinity is not really clear. There has been some recent work where they prove that this what else is uncountable, and they conjecture that even this what else has Hausdorff dimension 2. So this is kind of new. This paper came out maybe 1 or 2 years ago. So yeah, 2019. And if you define this kind of spectrum, C infinity X, where X varies over R2, this is going to be a subset of 0, 1 containing both the endpoints, but nothing is known about this as compared with maybe the Markov spectrum, if you know what that is. So the point here is that this set Di infinity has not really been given much attention until now. Okay.
You're looking at the set D. Wait, so the set D infinity. You're saying that it's not necessarily the full interval.
I don't know what it is.
And suppose we were. I see. Okay. So it could be. So it's always less than 1, but. Okay. Nice
for example, I don't even know if it's closed.
I see.
Maybe if you thought about it, I don't know what to say. I mean, pretty much nothing is known about this.
So the corresponding question for one dimension, it is the full interval, if I remember correctly, right? So there you're just looking at.
I don't. I think maybe okay. So don't quote me on this, but maybe in the 69 paper it would be proved there that it's everything, but I don't really know, actually, even in the one-dimensional thing.
Okay.
Yeah, okay. Okay, but the upside is that there was this other work where rather than considering the infinity, Akhundzhanov and Shatskov introduced the two-dimensional Euclidean Dirichlet spectrum. And there, so you make the same definition where you say C2x is this lim sup as t goes to infinity of t compared with the distance of q in integers going from 1 to t, and you compare it with the standard lattice. Let me draw it in a different color. Maybe here's the standard lattice. And what you're doing now is, rather than considering squares, you consider just Euclidean distance, and that's the thing you compare with t. You square it and then you compare it with t. So you can define this Euclidean Dirichlet spectrum, and they did that, and they proved that in this case, it's everything. Now, don't ask me about the proof, but it uses some kind of theory about best approximation vectors in R3. But anyway, moral is they were able to prove something. Maybe not for the infinity norm, but at least for the Euclidean norm, they could show this, which is progress, I guess. Okay, so we sort of saw this paper some time back, and we wanted to do something related to this result, because we had sort of been looking at effect of changing norms in Diophantine approximation, and here was this result using the Euclidean norm, so we wanted to say something. Okay, so we are going to work in slightly more generality. So still we have the Davenport-Schmidt result in mind. What we're going to do now is forget sup norm, Euclidean norm, just define any norm, nu, and define this quantity C nu x, again, this Diophantine quantity, this uniform Diophantine quantity, in exactly the same way. Rather than taking squares or circles, just you're free to choose whatever norm nu you want, use that distance, and then compute this, this C nu x. And we're going to define C nu as the maximum possible, or the supremum of all C nu x as x varies in R2. And we define, as before, this generalized new Dirichlet-improvable set is a set of all x in R2 such that C nu x is less than the supremum. And the theorem here is almost exactly the same as Davenport-Schmidt's theorem. So di nu has Lebesgue measure 0. On the other hand, it has full Hausdorff dimension. Dimension 2, again, it's dense, dimension 2 everywhere. And of course, okay, before that, it's not so hard to see that C nu is always going to be finite. So we'll talk about that a little later. And additionally, we can say something about the spectrum. The top of the spectrum, C nu, is not an isolated point. So it's an accumulation point of the spectrum. Okay.
Sorry, you have to tell me what new spectrum means here. Can you?
Yeah, so that's a good point. D nu is just C nu x such that, or script D nu, such that x belongs to R2. And again, of course, it's a subset of 0, C nu. So it just generalizes the definition from before. Okay, so it's the same theorem as Davenport-Schmidt, and in fact, the proof also sort of rewrites their proof in a different language, maybe in a more convenient language, and with some twist. Okay, So the way we are going to do this
So
is by
do your
reducing
techniques
to
also,
dynamics on the space of light.
do your results also extend to nu equal to infinity, or?
Yeah. I mean, it sort of reproves their theorem in a different language.
All right. Now, their theorem was in, okay, so now I'm a bit confused. Their theorem was in nu equal to 2, right?
So, Akhundzan of Shotskov, it does not, we do not prove this. Sorry, let me scroll up. Okay. So we do not prove this, but we reprove Davenport-Schmidt's theorem. I shouldn't say reprove, I mean, yeah, just.
But for example, is it obvious from Davenport-Schmidt that one is the limit point of points from the spectrum? I guess it's.
I mean, maybe not, but in essence, we will see why one is the exact limit point of the spectrum.
Okay.
Yeah,
I think I'm interrupting you too much. Maybe I should shut up. But,
it's fine.
Please
it's
go
fine.
on.
I mean, no. It's fine. We don't have to get to the end. I mean, no, like there's way more material here than we can cover anyway. So might as well like understand like 100% of what we see rather than like 50 or 20% of like everything.
That's my intention.
Yeah. Okay. Okay. Yeah. So we are going to maybe do this theorem in a more slick language about dynamics on the space of lattices. Okay. So X belongs to di nu. It's very easy. I mean, you have to think about it a little, but X belongs to di nu if and only if there is some C square less than the top, C nu, such that this holds. Yeah, you can multiply these together and see that this is equivalent to the lim sup condition. But essentially what we have here is this vector in R2. We're applying the norm to it, either the sup norm, Euclidean norm, whatever. We want it to be less than C over square root of t, and we're only allowed to iterate X up to t. So this always has a solution for all sufficiently large t. That's the condition for X being directly improvable. Okay, let's rewrite this by first defining Ux is going to be X embedded into this upper triangular matrix group. I want X1 and X2 here. And lambda X is going to be the lattice generated by Ux. So if you look at a typical point in this lattice, you take any integers over here. I'm taking minus P1, minus P2, doesn't matter. You multiply them through, it looks like this. So kind of looks like what's going on over here. Okay, so we can rephrase Dirichlet-improvability to this intersection condition in R3. I have lambda X, and I want to find a non-zero vector of lambda X, something like this, which belongs to this eta ball of radius 1, maybe dilated by some factor. Okay, so remember, nu is this fixed norm in R2. Eta is the norm defined by nu in R3, given by the max of nu and absolute value of the third coordinate. So if you're wondering, the norm ball, the unit norm ball for eta is just going to be a cylinder, I guess of radius 1. So cylinder over the base ball with norm nu. And then what this factor is doing, so think about it, we want this to hold for all t sufficiently large. So when t is large, the xy coordinates are going to shrink and the z coordinate is going to increase. So the effect is that this cylinder becomes really, really thin. And if this cylinder has non-trivial intersection with lambda x for all sufficiently large times, then x is Dirichlet improvable. Okay, so now maybe it should become obvious that C nu is finite. Okay, so why is that? First thing I want to point out is that this lattice has co-volume 1. Okay, second thing I want to point out is that this thing is a symmetric convex domain. So if you've heard of Minkowski's convex body theorem, that says that if you ever have a symmetric convex domain, maybe open with volume greater than 8, then it will definitely intersect any unimodular lattice, covolume 1 lattice. So all we have to do is to choose, c squared times this greater than 8, and then every x will be, c square directly approximable, something. Okay, so I hope that convinces you that C nu is finite. But we don't know the exact upper bound. We have like some upper bounds, but we don't know the exact upper bound for how large C square can be. Okay, now I want to change things a little more. I want to do this change of variables, which is called Dani's correspondence. So bear with me. This is an extremely fruitful change of variables, but it just takes maybe a couple of minutes to go through. Okay, so I'm going to define this one parameter subgroup of matrices, of course, determinant 1, and it expands the xy coordinates, it shrinks the z coordinate. So remember, we had this really thin cylinder. What I want to do is I want to normalize it. I want to transfer some of the motion from the cylinder to the lattice. Okay, so I have some intersection condition for Dirichlet improvability. I can multiply it by an automorphism of R3, in particular this automorphism. And if I choose S very cleverly in terms of T, I'll see that this matrix becomes diagonal with the same entry on the diagonal, or in other words, it becomes a scalar multiple of the identity. And that scalar multiple is actually c to the power 2 over 3, and I can just move the constant into the norm. So now we have this Dirichlet improvability as this as lambda x in the space of lattices should intersect this norm ball for all sufficiently large times. So notice if t goes to infinity, even s goes to infinity. So this is some 1-1 correspondence between the parameters. Okay, so yeah, so maybe the thought experiment here is we know there's an upper bound on how large c square can be when this condition will always hold. We want to see what the exact upper bound is. Okay, so for that, I'm going to make a definition.
Sorry, so just to go back, can you go up again? So equation 3 was the condition that, so what was equation 3 capturing? Equation 3 was, okay, so now I'm a little mixed up, so you will have to help me a little bit if you want. So is, okay, so we care about Dirichlet improvability. And for a certain C, yeah. So yeah, what's going on? Can you? I'm really confused. Yeah.
I don't blame you. So okay. So I mean, so hypothetically, let's just say we have C nu. It's finite. We definitely know it's finite. It exists. So let's say something is Dirichlet improvable, then this condition holds. Okay. So that means, so is this clear from the previous condition, the system? Yeah.
Sure.
So this is an intersection condition. So all I'm doing is multiplying by AS. that should also be clear. But then choosing S carefully gives us this. Now I might have confused everyone by trying to vary C, but let's maybe forget about that. So I hope at least till here we're all okay that Dirichlet improvability with the constant, C square less than C nu is equivalent to this intersection being non-trivial for all S sufficiently large.
Yeah, I think I understand this.
Yeah. So then maybe I came in and like confused everyone because maybe I was doing two things at once. So one aspect is what I hope is clear is the equivalence of Dirichlet improvability to this condition. The second aspect is I want to sort of rethink about what C nu is. I want to get an actual, handle on it, not just say, okay, it's some finite quantity that exists. So I want to see, how large C square can be. So maybe this is what confused you, but I'm saying it again because I want to know something about C nu, right? I mean, Akums and Schatzkov said it's like 2 over square root 3. Where are they getting this constant from? Okay, so okay, so I want to see some constant such that if C square is greater than some constant, then this condition always holds for all x. So something like that. Okay, so for that, I'm going to make this definition, critical radius. So we're going to do dynamics on the space X3, which is the space of 3-dimensional unimodular lattices identified with this homogeneous space SL3R mod SL3Z. Via the map, you take a matrix and just apply it to the standard lattice. So that gives you all lattices, and this stabilizes Z3. Okay, so I want to define this R eta is the maximum possible radius I can have such that there exists some lattice for which the intersection is 0. Okay, I'm going to call this the critical radius. So this is definitely one upper bound for this C nu candidate because if I have something greater than R eta, this condition is always going to hold because there's no lattice that intersects it at 0. So this is just a game I want to play to sort of see how large this C square or this R can be. So what is the largest ball I can have such that there is some unimodular lattices, maybe not a lambda x, but some other lattice that intersects the ball trivially. Okay. So I'm going to call this the critical radius. Again, R eta is finite, Minkowski's convex body theorem. And if you think about it, when eta is the supremum norm, B eta 1 is just this, box. And it has volume 8. So of course, the standard lattice is going to intersect this trivially. But you go higher than that, it has volume greater than 8. So then everything is going to intersect it. So is that clear that R eta is 1 when eta is the supremum norm?
Yeah, I think it's very clear.
Okay, great. Okay. So in the space of lattices, for the norm eta, I'm going to define the subsets K eta R is the set of lattices which avoid B eta R. Okay, so somehow this is related to Dirichlet improvability because of the condition we had before. So I'm going to define these subsets. Let's think about these subsets a little. Okay, fine. Okay, first thing. If R1 is less than R2, and I have a lattice which avoids the bigger, so I going to draw some norm balls. Let's just say we're in R2. This is radius R1. This is radius R2. If a lattice intersects BR2 trivially, it's going to obviously intersect BR1 trivially. So R1 less than R2 means that this K R1 contains KR2. And then if you go higher than R eta, you get the empty set. So it turns out that these things are shrinking targets of this non-empty compact critical locus L eta. Let's call L eta the critical locus, K eta R eta. So maybe there's the compactness is coming from a result of Mahler, maybe not so obvious, but there you have it. They are compact. And the fact that this is non-empty also follows from some argument of Mahler. Okay, so as R, okay, oops, R eta. As R goes to R eta, these things are shrinking to L eta.
So I kind of lost you for a bit. So Mahler's compactness tells you that K eta is compact.
That L eta, that this is compact.
But
Okay,
K
I mean, let's just see why. What is your question? Do we want to see that this is compact, or?
So is that compact? K eta R, is that a compact set? It is, right? Because of Mahler.
So I mean, exactly.
Okay,
so there's a uniform lower bound on the smallest vector. Yeah.
Yeah. So I get that. After that, what you said about trajectories, that is where I checked out for a bit. So can you repeat that?
What I said about what? About the L eta or something else?
So you said something about shrinking targets or stuff like that. I kind of just checked out. So can you repeat that?
Okay. The shrinking targets thing just follows from this. I'm just thinking about what the picture is as R goes to R eta. And it turns out that, okay, if R is pretty large, it's going to look like this. If R is closer to R eta, it's going to look like this. And if R is very close to R eta, it's going to look like this. If R is exactly R eta, it looks like this. And then it vanishes.
Okay.
Yeah.
Okay.
Because after R eta, every single unimodular lattice is going to intersect this non-trivially.
Yeah.
Okay.
All right.
Okay. Okay, so we're aiming for the, okay, so I have 5 minutes left. Let's just try to finish this proposition and then we can stop. Okay, so I want to show this thing. So for almost every x belongs to R2, if you look at the forward trajectory of lambda x in the space of lattices, so you have x in R2, it gets embedded as a lattice lambda x, and then it flows in the space of lattices somewhere. So this over here is as lambda x. So for almost every x, I'm going to draw this critical locus somewhere here in orange, this L eta. So for almost every x, there's going to be a certain point after which the orbit always avoids some open neighborhood, or I'm so sorry. What I want to say is that for almost every x, you can find.
Hey, Anurag, we don't see your screen anymore.
Yeah, I seem to have stopped sharing. Let me try it again.
By the way, was it, don't you want these orbits to, yeah, you should first start sharing. But my question was, don't you want these orbits to visit L eta? Avoid. Okay, so then I have misunderstood something.
No, I said avoid, but you're right. You're right. I mean, they're both important. Both properties are important. So okay, so I made a mistake.
So being avoiding it is like having X which is well approximable, and hitting it is being badly approximable, right? That the distinction? Or?
Yeah, so exactly. Avoiding it is directly improvable, and hitting it is not directly improvable. So what I'm trying to say is that for almost every X, you will find a sequence of unbounded times Sn. So here's maybe as1 lambda x, and here's as2 lambda x, such that these things converge to the critical locus. So the orbit is going to be chaotic, but for almost every X, you're going to find some subsequence or some unbounded set of times for which this ASN X converges to some critical lattice in L eta. That's the typical behavior. And this actually shows that the guess for the upper bound is sharp. The C nu is actually exactly R eta cubed. Because we've identified the typical behavior, and that typical behavior exactly corresponds with the R eta thing. Okay, and then we have the perfect correspondence once we show this, that X is directly improvable if and only if eventually the orbit avoids some neighborhood of L eta. So yeah, the directly improvability now has this perfect equivalence in terms of flows on the space of lattices. Okay, so questions about what the theorem is saying? Okay. Okay, yeah, so something is directly improvable if after a certain point, you avoid the critical locus. Now this after a certain point is actually quite relevant, because we'll see that sometimes lambda x starts on the critical locus. So that's why we need the stipulation of after a certain point. Okay, so let's see how to prove this theorem or proposition. Okay, so X3 is a non-compact homogeneous space, but it has a left invariant radon probability measure. That means inner, outer regular compact sets have finite measure. And this left invariance implies that any open set has positive measure. So we're going to use that. Additionally, you can show that this action, R cross X3 to X3, S lambda goes to AS lambda, is ergodic. So that's a technical term, but what it means is that there's no non-trivial in terms of measure set where the action restricts to itself. So that's roughly what ergodicity means. A consequence is that any neighborhood, in particular, any neighborhood of L eta, almost every lattice in X3 has a property that the orbit will visit this V for unbounded times. So that's a consequence of ergodicity. And now let me remind you, what we want to show is that this almost everywhere property for X3 can be restricted to this two-dimensional subset of lambda x. So that's what maybe the difficulty. I shouldn't say difficulty, but it's what's left. And in fact, that's not very hard at all. So you can show that this almost everywhere property is inherited by this submanifold in X3. These lambda x's, with respect to the appropriate measure. And that will show that for almost every x in R2, there's an unbounded sequence of time such that the orbit hits some or converges to a critical lattice. And that shows that the typical behavior for x is that it's not directly improvable. So di has measure 0. Okay, and if you're wondering how this inheritance works, it just works by the fact that this is the full expanding group for the flow AS. So if you look at maybe the Lie algebra and the action of this diagonal, on the Lie algebra, you'll see that you can, the Lie algebra of SL3R is diagonal, and then you look at positive and negative eigenvalues for AS, and then these turn out to be the positive ones. So you use some kind of geometry along with the ergodicity to show this theorem. Okay, so maybe once we've done that, I'll just talk about this last slide, and then I'll stop, or maybe I'll stop here. Yeah. Okay. So questions.
Thank you, Anurag, for the wonderful talk. Let's first thank you, and
yeah, thanks.
The floor is open for questions. I did half your talk, so sorry about that.
No, it was fun.
So can you say a few words about the Hausdorff dimension?
The Hausdorff dimension of what?
So you prove. So your theorem also proved that it has measure 0 and has Hausdorff dimension 1.
Okay.
Is that
so? It's Hausdorff dimension 2. It essentially follows we're not going to prove from scratch that BA has Hausdorff dimension 2. That was already proved by Schmidt, using his Schmidt games and stuff. But what we show is that BA is contained in DI infinity actually by using this equivalence. So what happens?
So didn't you prove that DI nu also had? So didn't you also have that DI nu has Hausdorff dimension? Okay.
We prove exactly the same thing.
I see.
It boils down to sort of this one fact in the space of lattices, that if you look at the critical locus L eta, it always consists of forward or backward divergent orbits. So you can never have a badly approximable lambda x with lambda x approaching L eta, because these guys are shooting off to infinity either in the plus or minus direction. So very quickly, that comes from geometry of numbers. The thing for what Davenport-Schmidt used in a different language, they use this theorem. It shows that this is L infinity. Always contains a lattice which goes to infinity in plus or minus direction. And essentially what we had to do, maybe the work we had to do, was show an analog for other norms. So again, critical locus always consists of lattices which go to plus or minus infinity.
I see.
Which go to infinity in plus or minus direction.
Other questions? Okay, so thank you, Anurag. Yeah, go ahead.
Thanks a lot.
No, this was wonderful. So maybe I should stop recording.